All right, good morning. Welcome back. It is Wednesday of sixth week of this strange quarter four virtual learning adventure. Um, yeah, and you all are doing awesome. Um, just to point it out, we had this 4-day weekend in the middle of the virtual learning quarter, and who knows what happens after that? Like, things could be different. And I, I'm just going to speak to the Block 1 Chem class and Block 3, both. Um, you're still doing it. You're still totally doing it. Um, Lots of people showed up to say hi to each other at 8 in the morning. Lots more people still showed up on the calendar doc to click the links right at 8 in the morning. Uh, you're building a community, is what you're doing, and you're learning some chemistry along the way, um, and it's awesome. It's really cool. It's really great. It's really like nice to see you doing this. Um, and Black 3 as well. We had tons of people back after the 4-day weekend, which is really cool. And if you're watching this and you don't join the class, welcome. and, um, yeah, it's just really cool to see everybody kind of like being there for each other. Um, yeah, and if you're thinking about joining us and you're like, would that be? You're always welcome. Whenever, however that looks for you, you can always join. Um, yeah, but congrats, and keep it up, and like not only through this class but like through life. Like, who knows what else is gonna hit us along the way. And I think this building community thing is actually pretty darn important. Um, yeah, keep supporting each other and reaching out and being supported, and yeah, I think it's really cool. You guys are doing awesome. Right. Yeah. Let's get to it. Speaking of being the second half of quarter two, we are quarter two, four, whatever, second half of the quarter. We're into the gas behaviors. Let's see here. So yesterday we looked at some like general gas stuff. We looked at your balloon, some stuff that you can observe about your balloon, some things we can measure. So we did all this stuff yesterday. Um, some things about how particles behave, your kinetic molecular theory. All right. Cool. We're gonna keep on keeping on. Today's stuff, um, typically what I do on today is we look at the relationships between the variables. So cool. If you've got the packet, we're on page 62. If you do not have the packet, we'll put this all on a piece of paper anyways. I'm showing you mostly so that you can kind of see just generally what we're looking at. So we're gonna be looking at as something. Uh, oh, and here's the things that we're gonna put in those blanks. We're gonna put these variables into these sentences. Okay, off we go. Okay, I'm gonna write this on a piece of paper just like usual. So these are gas variable relationships. And let's just choose some stuff. We'll just take it from the top. We're gonna compare. So compare the relationship between, just taking it from the top, pressure and temperature. No, volume. This is what we had, pressure and volume. Here's the sentence. And we'll think this through also. So as the pressure increases, And what you're thinking about there is you have your balloon, and you're gonna squeeze it. You're gonna increase the pressure on your balloon. Okay, so you're squishing your balloon. As the pressure increases, the volume decreases. You just squished it. You just made it smaller. As the pressure increases, the volume decreases. And we can do that in reverse also. So let's say we're going to take that pressure, and instead of squishing the balloon, now we're going to expand the space around the balloon and decrease the pressure. So as the pressure decreases, the volume will expand to, will increase to accommodate. So as the pressure increases, as you squish it, the volume decreases, gets smaller. As the pressure decreases, the volume will increase. And we call this also, and these will just be, and one will do increase and the other will do decrease. Let's look at the graph. As the pressure, and you can do these either way, pressure and volume. As the pressure increases, volume will decrease. As the pressure decreases, the volume will increase. It's something that looks kind of like that, just real generally. Is that inverse or direct? That is an inverse relationship. The slope goes down. Inverse or direct. And then what does a constant look like? So if P is big when P is small, and V is big when P is small, I'm going to give you this, and we'll start to make sense of it. If we multiply them times each other, that will stay constant. So a little amount of pressure, big amount of volume, little amount of volume, big amount of pressure. And this, you're just going to kind of take my word for it for right now. And then when we see some directs, we'll see what a direct kind of math relationship looks like also. We would typically do a lot of labs around now. Yeah, I can try to link some of those too. That would be a good idea. I should link you some labs. Yeah, let's just keep crunching these. There's kind of 3 sets here. So we did pressure and volume. Let's do pressure and temperature. And this is sometimes easier to think of as the temperature, because that's what we're used to thinking about. And pressure, but you could do this either way. Actually, let's do temperature and volume. Okay, this is easier to think of. Off we go. As the temperature, they would usually say to you, what do you want to do to your balloon? Do you want to put it in a snowbank or in the oven? Or don't do these things, right? But let's go there. If you're gonna increase the temperature of your balloon, so imagine you've got a bonfire or something like that, and you're going to put your balloon nearby it. Again, don't do this at home. But if you were to increase the temperature, the volume, is that balloon going to get bigger or smaller? And you're doing this mental activity because you're like, obviously, this thing is going to grow huge and then eventually pop. And that's why it's somewhat, because now you have rubber flying in your fire, which is not a good thing. This one's a bit safer. Let's take it the other way. So sometimes when we do this in the winter, as the temperature decreases, we can go out the back door at Pim and stick our balloons in a snowbank and decrease their temperature. and observe how the volume changes. So as we drop the temperature, your balloon shrinks. You could try this at home. This one is one that you can totally do. You can take a balloon, inflate your balloon, put in a certain number of particles. So once you tie off your balloon, you're not changing the number of particles anymore. That will stay constant. But take your balloon, drop the temperature, put it in the freezer, and it shrinks. It turns into a little tiny peanut balloon. I don't know if you've done this before, but it gets real small and squishy, and you in your mind, you're like, it looks like we've deflated it. It looks like we took out air, but you tied off that balloon. The balloon is now not changing how many moles of air are inside anymore. What did change is the temperature. We said yesterday temperature is motion. You made it cold. Particles stopped moving. And the appearance, the effect is that the volume looks really slow, just because the particles are being lazy and cold and stuff. I'll take that over here as well. So as your temperature increases, your volume also increases. There we go, that's what that is. High temperature, high volume. As your temperature decreases, your volume decreases. It's something kind of like that. That has a positive slope, that's a direct relationship. And your constant here, so we want this to equal a constant, and we're going to say that as volume increases, temperature also increases. You could write this the other way around. You could say T over V is constant, but basically as this grows, this also grows. As this shrinks, this also shrinks. To keep that constant, we're going to divide the numbers by each other. Don't worry a whole lot if this, I'll help you take the next step here. But I want to show you to kind of start making the link of how the relationship becomes math. So this right here, this constant idea, is how the relationship becomes the math. We'll do our last one. What have we not done yet? Temperature and pressure. Okay, and let's think about it as changing the temperature again, because that's just easier. So we'll start by increasing the temperature again. Again, imagine you're over a campfire or something like that. Same thing here. You heat that up, particles are going faster, that is a higher pressure situation. Same thing in reverse, put that in the freezer, that balloon that looks real deflated, that's a drop in pressure and a drop in volume. That kind of flat, flubby looking balloon in your freezer. You drop the temperature on it, and now both the volume and pressure have dropped as well. Okay, these two relationships look somewhat similar, right? Same thing here. As your temperature increases, your pressure also increases. As your temperature decreases, your pressure also decreases. Again, another direct relationship. And again, that constant thing, as you increase pressure. Oh, you can do it that way too, like your pressure cooker. If anyone has ever seen a pressure cooker, as you increase the pressure, the temperature inside also increases. You are able to, for example, boil water at hotter than 100 degrees Celsius if the pressure is really high. You can keep those really fast-moving particles liquid longer. This is how you get molten rock in volcanoes and stuff like that. It's got the pressure of the crust sitting on this molten rock. And because those fast-moving particles are squished, they have high pressure on them, their temperature is able to increase a whole lot. A lot. Become molten rock. Yeah. That's that. Just summarize, we kind of thought about changing pressure, squishing things, changing temperature, thinking about them in the freezer or in a hot situation, like a hot environment. How does the pressure and volume respond? You see this also in the winter in your tires, the trap sample of gas that you use all the time. As the temperature decreases, you probably notice every winter that your tires get really flat and you have to go refill your tires. Similarly, in the spring, if you have somewhat flat tires, you know that the temperature is going to increase. It's going to become summer. I would not put more air in your tires right now. I mean, like, if they're super flat, put more air. But, like, the temperature is about to increase, so also the volume and pressure inside your tires are about to increase. Yeah. Oh, also, if you take your tires out on the highway for a long time, that increases the pressure, which will also, I said the wrong word, that increases the temperature. The friction on the road increases the temperature, and that'll increase the pressure a little bit also. Yeah, those are a bunch of relationships. That conquers this page. Okay. Good. If you are in the packet, you will notice that this page comes next. Although for our virtual learning world, we're gonna skip this for this particular moment. We are going to go here. Page 65. Don't worry if you're in the packet and you've got that page with like all that stuff on it. We will come back for that tomorrow. But I'm thinking for right now, it's going to make a little bit more sense if we do Charles' Law, doop-a-doop, never heard of this, that's okay, first, and then come back to all those letters on that other page. Yeah. So this is going to be our first foray into mathing with gas. But don't worry, you got this. We've got our relationships. We've got our math. And that's actually all we need. You are now fully set, but don't worry, we'll do some together also. I realized I should put this in the example video, which I will do. Let's get you one more kind of note level thing before we do our first example. We are, surprise, we're going to be doing some conversions. Let's call these gas conversions, though they're not restricted to gases. They will also apply to other things. For example, this is a conversion that will apply to other things as well. Off we go. We've got pressure, volume, and temperature. Let's keep them in the same order as the first day. Okay. We're going to do a reverse order from the first day. Temperature. Just because you know temperature in your everyday world, like more familiarly, you know more about temperature. Just from being alive. Pressure and volume sometimes seem a little bit more abstract. Temperature, we're real accustomed in the US to using Fahrenheit. Just put a big X through that. Divide by 5 nines plus 32 or something along those lines. Don't just put an X through it. You know from past years that Celsius is the science unit of temperature, which is totally valid. You know that 0 degrees Celsius is freezing, 100 degrees Celsius is boiling of water, and 1 atmospheric pressure on Earth. Cool, well, anywhere, but 1 atmosphere of Earth. Yesterday, we got into a little bit how temperature measures energy and motion, and we kind of want a scale in which all energy and motion are seen as in the like positive number realm, because negative motion doesn't, I mean, you can go backwards, but we don't think of forward and backwards with gas particles. Like if they're moving, that motion is like like we're on a scale where it's all positive numbers. Things get real funky if you've got negative things involved also. So we've got a conversion from Celsius to Kelvin. Off we go. And that is, you're going to take your degrees Celsius. This one's real easy. Add 273 to find your temperature in Kelvin. If you have a temperature in Kelvin and you want to take it back to a temperature in Celsius, minus 273 to get a temperature in Celsius. Let's put some real world stuff on this so it makes a little bit more sense. We're going to do room temperature is 25 degrees Celsius, so like, I mean, you could be in any room at all right now, but we say just kind of general room temperature is 25 degrees Celsius. And we'll practice here, so plus 273 to get to Kelvin, so that all motion is considered positive. And there you go. 298 Kelvin is room temperature. Your body temperature, I think, is 32 degrees Celsius, plus 273, about 305, did I do that right? Kelvin. 0 degrees Celsius, freezing water, plus 273. Water freezes at 273 Kelvin. Anytime you have temperature, you're going to convert it into Kelvin. So anytime you have temperature, convert to Kelvin. Every single time, 100% of the time. This is the most likely thing to mess you up. The number one thing is forgetting to convert to Kelvin. Luckily, the fix is just converting to Kelvin, which is adding 273 to your Celsius temperature. The fix is not difficult. The challenge is remembering that you're always going to be in Kelvin if you're working with the temperature. Alright. Up next, we'll just do these in reverse. Volume. Of these three, volume is the one that you are most likely to already be familiar with. We want the units of liters. Let's add that. So you want Kelvin for your temperature. You want liters for your volume. You are either going to be given liters or milliliters. So in case you're given milliliters, you're just going to do a single step domino conversion from the beginning of last quarter. You've done like so many of these by now. There are 1,000 milliliters in 1 liter. That's all. I mean, if I give you gallons, I'll give you a conversion to get to liters. If I give you moles, let's do moles also. Well, moles you're going to keep as moles, because that assumes standard temperature and pressure, which we're about to change. Yeah, this is probably about the most complicated that volume's going to get. Great. Here's your pressure. Pressure has a ton of different units. One of the interesting units is, I'm getting ahead of myself. Let's do this over here. PSI, which is like the most British thing ever, pounds per square inch. This is what your tires are probably measured in PSI, as is your tire pressure gauge. And I'm starting there, not because we'll ever use it, which we won't, but because it's easier to imagine because we live in the US and we think in terms of pounds and inches. So think about an inch square inch, 1 square inch. And so on this square inch of this paper, on this square inch of your flesh, on this square inch of everything around you on planet Earth, because we're on planet Earth, 1 square inch has 14 pounds of pressure on it. So think about the weight of your cat, or like that is like a decent size. Well, the cats come in a lot of sizes, but like on every square inch of every surface, there's 14 pounds of air just sitting on you, just because you're on the atmosphere of Earth, inside the atmosphere of Earth. If you want, when we're together, we will imagine putting like a plate or something like that on the top of your head, like a disc or a circle or whatever, kind of the size and shape of your body, balancing this on the top of your head. And you're going to think about the ocean of air sitting on you. So extending all the way up into the atmosphere. That atmosphere is full of air. Air actually has mass, like we talked about yesterday. Like all your air, 80% of your air has mass of 28 grams per mole, right? So like, but it has mass is what's the important takeaway there. And that mass pushes on you. So 1 atmosphere equals, 1 atmosphere is 1 ATM. Again, ATM now means atmosphere also. 1 atmosphere is 14 pounds per square inch on everything on the planet. And you may be thinking, how do I not notice? You don't notice because, well, first because you evolved here and you've never been anywhere else. That's why you don't notice. But also, temperature is motion. We live in an environment more or less at room temperature-ish. Everything is in motion. You've got that same 14 pounds per square inch pushing both down on you from the ocean of air above you and also up. All those particles are still in motion. They don't stop moving just because they're on the other side of your body. You have equal pressure on all sides of you all the time because all of those particles are in motion. They don't stop. They've got that same motion from their temperature that causes that pressure all around you. So it's not just sitting on your head. It's also pushing on every side of every part of you and everything you have ever known, unless you've left the surface of Earth, which is unlikely. Well, I mean, if you scuba dive, then you get even more, pressure, excitement going on. But that gets into fluid dynamics, which eventually we'll do. But for here, let's just think about the atmosphere. All right, so that's what it means that your atmosphere has pressure. Gas is heavy. It is, in fact, fairly heavy. And we just call that 1 atmosphere is kind of the average pressure at sea level, blah, blah, blah. Okay. Your atmospheric pressure can change. You may know this if you have, joints that, pop right before a thunderstorm. As your pressure drops, sometimes that can, funk with stuff inside your body also. You may or may not know somebody who can say, I can feel a storm coming. Probably pressure related. They probably have some system in their bodies that responds to the lower air pressure. So 1 atm is kind of the average, but it does totally change. Your barometric pressure, your weather people talking about the air pressure that drops before storm, blah, blah, blah. I shouldn't say blah, 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 but it's real. It's really interesting. That's pressure. I forgot where I was going. while it would seem to make sense to keep everything in ATM, that is actually not a metric unit. However, getting to your metric unit is fairly simple also. So we want pressure in the metric unit of kilopascals, which you've never heard of, which is fine, except for yesterday. So we want it in kPas, kilopascals. A pascal is related to force in newtons divided by area in meters squared. If PSI is super British, kilopascal is super metric. Whatever. Okay. So kilopascal is 1 newton per meter squared. Great. Newtons, by the way, are really tiny. If you poke your paper, that was probably 5 newtons. So 1 newton of force is not very much. Also, 1 kilopascal of pressure is also not very much. Okay. So 1 atmosphere, if you're given atmospheres and you're going to your supermetric kilopascals, set your conversion up like we've set up every conversion the whole year. Just gonna do a little break there. Okay, right. Looks good. 1 atmosphere is, we're gonna use 101 kilopascals. Technically 101.325, but let's just go with 101 for now. Yeah, kilopascals are super, super tiny in amount. Atmospheres are pretty substantial in amount, and in fact, 1 atmosphere is 101 kPa. All right. Whew. There you go. Got your relationships, got your conversions. This may seem like a lot. We are about to take it here, which I think I've already shown you, and I will do an example in the next video.